Hello everyone, in this video I would like to show how can we implement a closed-loop position control by using Siemens 1200 PLC and the DC motor. I'm using Siemens i7 1200 PLC, which number that is a 1211C. And since I'm using the lowest end of the controller, that means once you use the Siemens 1200 PLC, you can also implement this closed-loop control system. Okay, so in this case, I'm using this controller running as a Profinet master here and connect to this station. So basically, this station run as the analog output because this controller, it doesn't have a built-in analog output. This is not our focus in this video. So the main idea for this module, it can output 0 to 10 watts, or basically we will control 0 to 5 watts from this module to this PWM module here. So this PWM module, the power I connect to 24 watts. And this is the motor, 2 wires. And these 3 wires that come from this analog output module. It receives 0 to 5 watts and adjusts this motor speed using PWM. So let's look at this motor. This motor, I connect to this small DC motor, and it has a gearbox. And from this gearbox end, I'm using this back of this encoder. It has 1024 lines per revolution, running at the speed and the closed loop positioning feedback. Okay? And then the encoder signal, it has A and B signal. So the A and B signal are wired to the input 0.0 and 0.1. So this configuration also very simple. I will show this after. So these 2 signals come from the encoder A and B. Basic idea, the input of this PLC come from the encoder A and B, go to I 0.0 and I 0.1. And output, we are using the analog, control the PWM module and control the motor. And voltage, that is a 24 watt. In the actual industry case, maybe you are using the VFD. Actually, this PWM module running the similar role as a VFD. So you can use the analog output control to control the VFD speed and control the motor speed, right? And using the encoder. So the encoder only high end. Basically, we only need A and B. Incremental encoder, that's enough. And connect to the PLC. We do not need any specially encoder reader module. So this 1200 PLC is built in couple channels for reading the encoder. All right, let me show how can we use TI Portal software to implement the positioning control by using this hardware, using the analog output and the encoder feedback, set up this closed loop control system. Let's shift to the software side. Let's open TI Portal version 16. You can also use the TI Portal version 17 if you have a lower version. So the common version, what I'm using, is TI Portal version 16. Okay, I will create one project named i7 1211. This is the lowest end controller using AO control and encoder as a feedback. We are doing the motion control. I will use the motion control access to set up this closed loop positioning control loop. Okay, let's create. Let's shift to the project view. Okay, let's firstly click this add new device. Let's start from the scratch. Especially this is the case for the new learner. So if you follow me, basically you can set up this closed loop system in 10 minutes. So let's pick this unspecified CPU so we can upload the correct number, the correct type. And let's set up this unspecified. Let the system automatically detect the actual hardware type. And from my laptop, I'm using the Ethernet cable connect to the CPU. Okay, click this detect. So we can online find the actual hardware. So click this start search. Our system find out this controller. So its type is a 1211, which is the lowest end. So once you have any other Siemens 1200 controller, you can implement the same function. Okay, which IP is 1.180. Okay, let's click this detect. All right, so the system automatically detects this hardware. So let's double click this Ethernet port just to do a double check if this hardware that's the same as mine. Okay, Since this controller doesn't have a built-in analog output, in this case, I'm using more that hardware as my analog output. In your case, you have multiple ways to implement the analog output. The simplest way, you can double click here, and from this hardware catalog, you can use this signal board and select this analog output module. This is a Siemens, a small analog output module. But I don't have this analog hardware in hand. Fortunately, I have this Profinet device. Also, this is a good time to show you if in case you have a Profinet device, how can we quickly set up the Profinet communication, right? Okay, so please follow me. Click this Ethernet port and let's initiate Profinet subnet. Then click this network wheel. Okay, this wheel. And then most of cases, if you are using the third end Profinet device, you need to install the GSD file. To install the GSD file, you can go to Option and click this Manage General Station GSD file. Okay, and then from this source path, browse the GSD file you can have. And in this case, I install this more device already. Okay, and after you install the GSD file, you can from this right side, this hardware catalog, find out the other field devices, find out Profinet IO. And in this case, I'm going to search the more. From this IO, this more device, Cube 20. Okay, I will drag this Cube 20 here. And to set up the Profinet communication from this square, this area, drag to the controller. And once you see the system set up this rail, this style, blue and white, this style, that means this device find out this controller from the hardware configuration wise. Okay, especially here, this PC_1 that represent here. That means this controller, this master, this is this device master. Since my CPU, that IP address is 1.180, so I will set up this device IP address as a 1.181. Okay, just the next IP. So double click this port, and we can go here and Ethernet addresses, and I can set up this IP address as 181. Okay, and then just to check out one thing, the Profinet name, the device name. This device name is an actual name, allows the controller to find out this device. So now I will use the system automatic generated name. Okay, and then now let's go to the right side. Let me quickly set up the hardware configuration. This hardware configuration need to match my actual case. Definitely in actual case, from your end, you won't use the same device. So this is just to quickly demonstrate. Okay, then one thing I would like to check, that is the analog setting. So from this analog, from this module parameters, just to double check our output, I need to assign to 0 to 10 volts, because the DC motor, that drive module, that's the PWM module, which input that actually from 0 to 5 volt. We just need to limit or set a lower speed, doesn't allow this module output higher than 5 volts. That's it, right? So I will assign that 0 to 10 volt. Okay, and for this high and low bias, I will use this Motorola because it's a Siemens style. Okay, default. All right, so we finished this hardware configuration, and now we can download this hardware. So let's firstly download this hardware, compile and download, and let's firstly set up this communication. Okay, search this controller and click load. Download this hardware configuration to this controller, to this CPU. Click stop all. We will stop the controller and reboot. And then to verify the Profinet communication, definitely this module, this is hardware. The hardware doesn't know which IP address, and it's a Profinet device name, right? So we need to assign that Profinet device name we set in our offline project. We need to assign this Profinet name to this device. Okay, so back to this hardware wheel. From here, right click, click this assign device name. Okay, double check this Profinet device name that comes from our offline project, and now we can click this update list. Okay, and then find out the device, just double check and click this device, and then click this assign name. After you assign successfully, your system will show OK here, and you will find your device IP address will automatically assign the IP address to this device. Because the Siemens, the Profinet, is using this device name, find out the device first, hardware device first, using this assign way, and then follow this device name. The IP address from our project configuration will be also assigned to this device. Then you will find your device has the IP address and the Profinet name. Okay. Now, if we click this Go Online, just double check if our system is running correctly. Everything shows green. That means this device can communicate with this controller. Now, this is a purely hardware portion. Let's go to the access control. Let's actually set up our precision closed loop system. Okay, click this Go Offline. And then let's go to the Technology Devices object. Click. Okay, so we will use the motion control. Let's click this motion control. And we will use positioning access. So default name, that's access. We can change the name that access DC motor. The DB name, we can use the automatic DB name. It starts from 1, which is fine. Okay, we can use the automatic name. Let's click OK. Okay, this access is running as the driver for the PLC controller. And this access plays a role connect or configure the drive system as well as the encoder system. Okay, so once we configure everything here, we do not need to care the encoder and the drive individually. We will use this access to help us to organize everything behind. Okay, so let's follow this wizard. Basic parameters, so access name, DC motor, and the position unit. As you can see, in my system, I'm using the analog output, so I will select the analog output. Okay, I'm using the analog as the drive connection. Okay, and then select the unit. My encoder directly mounted on the shaft output. So for the positioning control, we can see one revolution that's 360 millimeter, or we can call that degree. Okay, in this case, we can call that degree, which is quite straightforward, degree. And we won't use the simulation, we directly use the hardware. Okay, so this is the diagram. Now, this drive here, this is our PWM module. So we are using the PWM module to control the motor, right? And so the encoder will be mounted on the shaft end and directly feedback to the input, the high pulse input for the controller. Okay, and from this analog output here, we can pick the analog output. Since we haven't set up the analog tag name, so it cannot find out the analog output. Then let's go to the PLC tag, show all. So let's name the first channel. The first channel, that's the QW100. So we can name this is the DC motor PWM. We name this. Okay. If you recall, so we are using this analog output from this device, which address is 100 here. So we name this first channel, name that DC motor PWM. Okay, that's represent the first analog output channel. And after we assign this channel name, then go back to here. So using the analog as output, this time we can find out the channel from this job list. Here, DC motor PWM QW100. Okay, that's an analog output. Let's select that. Okay, and this enable, you can pick the digital output to enable the drive power. Basically, the drive there will be a contact or relay connect or control the main power for the module. So in this case, I'm using a very simple switch directly give a power or shut down the power. So here, I won't select that. In the actual case, most of the cases, you will pick the one output using that relay or contact to deliver the power to the drive, especially you are using the VFD. Okay, and ready input, the same thing. So you can pick the input direct from the drive, from the VFD, especially you are using the third end VFD. The VFD basically could have one digital input go back to the PLC, so you can use that digital input as a feedback, ready feedback from the drive, from the VFD driver. But in this case, let's focus on the closed loop control system. So I will especially only configure this analog output. Okay, this reference speed, basically that's the maximum speed of your motor can run. For example, in this case, that motor high speed, it can run 150 RPM. And my unit, that's the degree. So here I need to set 150 that drive system can go and times 360 degree, that's the unit, right? Per minute, take care, this is per minute. RPM, that means the revolution per minute, right? So we need to type in 54,000 here. Okay, and the maximum speed, that's our production wise, or basically from your application. So your application basically always lower than the maximum the motor can run. So for this case, if I assume I will allow my motor runs 120 RPM, that means the high speed, that is a 2 revolution per second, right? So I will say the 120 RPM time 360. So 200. Okay. We finished the drive configuration. And then let's shift to the encoder. So regarding the encoder, as shown in the picture, I'm using backup this encoder. Actually, you can use any simple encoder. So this encoder can give me 1024 lines per revolution. And I'm using the built-in high process input from this controller. So we do not need to purchase any additional encoder reader hardware, terminal, or module. So from this encoder here, I will pick this encoder on high-speed counter. The high-speed counter HSC, that means the high pulse from this PLC built-in input. And from here, that's the high pulse, the high-speed counter resources from this controller. And from here, we can see this small controller can give me 6 high-speed counter resources. So I will pick the first one. Which hardware input we can select here? As shown in the picture, we are using the 0.0 and the 0.1. That's the A channel and the B channel. And from this case, so we need to select two AB counters. Okay, so this is A channel and the B channel. Okay, and from here we can see this is the highest frequency. For most of the cases, that's enough. And take care of this. When we firstly set up the system, maybe you encoder the actual counter direction, that's the reverse with your actual spinning, the motor spinning. So we need to test it at first, and maybe we will check this invert encoder direction to correct the direction, the forward or reverse, which is very easy, just one checkbox. Okay, and here the encoder tab. So in this case, I'm using the rotary, the encoder, incremental encoder. So I will pick this. One revolution, 1024, and that's it. So per revolution steps. Okay, so that's enough. As we can see, for the drive, we are using the analog output. So I can pick the analog output channel. For the encoder input, we are using the AB, this simple style incremental encoder. We assign this hardware channel and assign the high pulse resources. And then let's quickly go through other configurations. So to let the system know where your encoder mounted, this basically allows the system know what the encoder represents. So for my case, my encoder mounted on the shaft. So we will see one revolution from the motor or from the gearbox. That is the one revolution for my encoder, right? So we will see on the motor shaft, And because my shaft and the incremental encoder, they directly mounted together, so one revolution on the shaft, that incremental encoder run one revolution. So one revolution, this is 360 degree. And the position limit, so for testing purpose, I won't select that, but in actual case, you probably need to select to enable the limit, so to prevent the over travel, okay? Dynamic, we probably can set the acceleration and the deceleration. And dynamic, that's the place to set up the default acceleration and the deceleration, as well as the maximum velocity. So in this case, I can use this per second degree. So 360, this is one revolution, right? So we can set the maximum velocity. Let's say the maximum, that's the 2 revolutions. We can set 720 per second, okay? And this is the acceleration and deceleration. Probably this acceleration is pretty low. I can set a higher, for example, 1000. Set a higher acceleration and deceleration. And this is the e-stop, this acceleration and deceleration. If you want your motor quickly stop, so you can set a higher deceleration, okay? So, and then click the homing. The homing, that's a very big topic behind, but to quickly show, I will select the simple passive homing, okay? Also, we can use our access that direct the home, set a 0 to the access, direct set home, okay? I will leave everything as a default. And then the positioning monitoring. Actually here, that's the important, especially for this following arrow. Take care, you need to take off, uncheck this selection at the early beginning, because at the early beginning, maybe your motor encoder that direction that totally reversed. Maybe your PID loop, especially the gain, haven't set perfectly. So when you control the motor, your feedback won't be followed very well. And if you check this, so the system will always show fault. You cannot test anything. So at the early beginning, you can take off this, or you can set this value very large. So you can set a very high value. Okay? Stand still. That's the place to judge if the motor totally stopped there without any moving. Okay? And closed loop here. So pre-control 100%, and again, let's leave the gain 10 as a default here. Okay, we are almost done. So now we can download this hardware. We can use this commissioning directly fire the motor, and we can see the positioning and feedback loop, that velocity and the positioning. All right, let's download. Okay, now let's start this controller. Okay, let's go to the commissioning and active this commissioning mode. So your controller, your program won't enable, because this panel, this commissioning panel will occupy that permission from your program. And so that we can focus on this panel. Okay, and enable the access. That's basically if you have an output to control the contact, so you'll see that output can be delivered. Basically, this enable, that's the same idea if you're using the program power on. Okay, and we can firstly use the jog mode. So we can set 360, very low speed, and let's click this forward and the backward, so we can verify the motor direction. Click this forward. So as we can see, if I hold this forward, I can see the velocity is increasing. Okay, that means my direction, that is correct. If you click this forward and you see the velocity showing the negative, that means your encoder direction, that is reverse with your motor travel direction. So then you need to go back to the configuration and go to the encoder here. You need to check this invert. So once it's on, it invert the internal value. So we can see the motor is running. Okay, the rough speed is running around 360. So we haven't fully optimized the PID closed loop. So we can see the velocity is running around 360 degrees per second, 1 revolution per second. And we can see the actual velocity from the velocity area. That's not an accurate device. After all, this is a test purpose. After all, this system is just a test purpose. Okay? Alright, basically this is the first step. You need to use the forward or backward jog mode to verify if the position speed that basically makes sense. Okay? And then let's enable again and go to the homing. So firstly, we can home or set certain value for our access. This is come from the encoder. So we can set 0 or some value we can set here. Okay, if I click this set home, if I set 0, so we can see this position will be overwritten. Okay, so we set 0 to our access. Okay, because this is the incremental encoder, so after we cycle power, we need to set a home to the encoder or 0 the encoder or home the encoder, right? The homing access, that's the big topic behind. I used a couple videos discuss this before. So after we home the access, give a value for this access, then we can go to the positioning. Keep in mind, currently we haven't set up any program. Using this panel, we can control the motor. We can read the position from this encoder. We can clarify if every setting are correct. But you can imagine now we can use this panel can run the motor, which is amazing. Without using the access, just to manually set up the motor. And the encoder, you need to calibrate everything, connect them together, program the PID loop, which is very complex. Using this access, basically we just do that in minutes. Okay, and for positioning, so we can set a target position, so we can verify if our closed loop, that gain parameter, or we can call that PID controller behind, if the parameter that makes sense. So we can set 1000, let's say, and velocity, that's a 360, so which is fine, we can use 360. And acceleration, deceleration, we can set a higher, for example, let's say 500, higher acceleration, deceleration. And now we can click this relative. Relative means every time we click this button, it will travel 1000 degrees. Okay, let's click this relative. Okay, it stopped at 972. And the system shows the target range haven't reached yet. So that means our PID loop that definitely need optimize. Let's try it again. So enable the access. Firstly, let me home the access, set 0. Okay, go back to the position. And let me set 2000. Okay, travel a higher speed. Let's say 720 degrees. Per second, it runs 2 revolutions. And let's run. So we can see the target is 2000, but it over travel a little bit. Definitely our PID need to optimize, need to tune. But keep in mind, since we are using the analog output, in this case, my closed loop system that located in the controller. This PWM module, this is poor device, its performance is the limit. And we don't have the current feedback loop from the drive system. What I mean, if you are using the VFD control system, the VFD controller itself, it has a current loop inside. It can optimize something to control the motor more accurately. In this case, I'm using this very simple system. So this accuracy won't be very high. So it's just a demonstration. All right. To quickly demonstrate how can we tune this, for example, this. So basically our PID need to be higher than gain. So from this tuning here, we can scroll down. We can see this is our gain value. Probably I can set a higher. For example, I can set 40 direct. Okay, and from this area, we can monitor the side point and the velocity feedback. Okay, and to quickly show, we can go back to after we set this gain here, and then we can go back to the axis. Let's home that first. Home the axis, And then let's travel 360 speed. Let's use the 360, that velocity, and let's travel 1000 again. Okay, let's click this relative again. So this time we can see it almost reaches the 1000. Okay, it just over travel a little bit. Okay, so I can tune a little bit, confirm this error, and enable again, and I can set, let's say 45. Let's say 45 here. Okay, let's again a little bit higher, and go back here, and let me home this axis again. Set home. Go back here, position. Let's travel 1000. Click this relative. Okay, we can see because I increased the gain, so it over travel higher. So that means my gain that too high. I can decrease the gain. It was 40, right? So I can shrink to maybe 35. So enable the access. So let's add 35. Okay, and then go back to the access. Set the access to 0 again. Confirm the fault. And let's travel again. Select the positioning control. Okay. Set home again. Okay. Then go back to the positioning mode. Same speed, same distance. So we can compare relative. Okay, relative. So we can see now it travel lower than the target. So probably we just need to increase our gain a little bit because we changed from the 45 to 35, maybe too high. Probably the 36 or 38 that's fit for this system. That's the rough idea how to tune this gain. So in this case, maybe I need to change to 38, for example. But as we can see, so we can quickly set up this closed loop system using the analog output and this encoder feedback. And this positioning control, that's basically done. And next step, we will use the program to home, jog, and velocity control and the positioning control. This is the program after. But basically, we can quickly set up this hardware entire closed loop, right? Home this again, home this axis again, and this time let's travel. Okay, so it become better, right? Confirm the fault. And then let's verify if the actual travel distance that match our actual case. So for example, if my target, I will allow this motor travel 3 revolutions. 3 revolution, that means 3 times 360 degree, right? So I need to type in 1080. And then from the video, let's verify if this motor travel 3 revolutions. Okay, now I can set 1080. And speed, that's a 360, okay? And before that, let me home that position. Let's assume the current position, that's the home position. And now, let's watch the motor, and I will travel 3 revolutions. Let's click this relative. Okay, as we can see, this motor definitely travel the 3 revolutions. And this position, basically, which is not too bad, this position. After all, we are using the DC motor and this PWM module. That's not a high-end control system, right? This hardware. And every time we will see this error in target range, so we can optimize our PID tuning as well as the configuration. We can open this monitor, this range. We can open up this monitor range a little bit, allow the system not too tight, give the system this accuracy more tolerant. After all, using the analog, especially for DC motor and the VFD, it won't be very accurate. We need to give the system a little bit tolerant. Alright, that is for this video. So we can see using this 1200, this small controller, is built in the high pulse input and analog output. We can quickly set up this closed loop control system. And using this access configuration, we can quickly set up the control loop and the feedback loop here, right? And then we can, using this commissioning panel, to quickly verify direction, position, encoder setup, and the position control. And once you figure out this, so the rest of things, we will use the program to control this. And then the next topic, how can we use the MC function blocks to control this access? That will be the next video topic. Actually, I used one video certain time before to show how can we set up the function block using the MC home, velocity, and the positioning control to set up one function block. For example, if I go to the OB1, so from this corner, from the OB1, this main control, and from this right corner, motion control. So as we can see, this motion control, we have a MC power, reset, home, halt, move absolute, move relative, and they are very common used for the motion control word. Alright, that's it for today. We briefly set up this positioning control using the DC motor and encoder feedback, as we can see, which is very simple. Actually, just use around 10 minutes, we can implement this closed loop system. Okay, next video, I will show how can we use this motion control command to control this DC motor. Alright, see you in next video. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.